In this video, I'm going to show the high-level service image of why we may need a DC coupling or AC coupling between the TX and RX in any serial interface. As you already know, in Microelectronics 101, any signal could be direct current DC or alternating current AC. Therefore, the DC coupling serial link means you can directly connect the TX output through a median, cable, or PCB to the RX without adding anything else in the interface as shown here. Obviously, there are no constraints in the transmission data or any passive component in the link. How about the electrical specifications of the TX and RX? Think about the common mode voltage or the DC level images for 5 seconds. Bingo! The DC couple interface is quite simple, but any TX should have its own output DC level and swing range. Similarly, any RX should have its turbo input DC level and input swing range in terms of their optimal DC operating point for workable amplifiers. Moreover, for most common I/O buffers such as low voltage positive reference emitter coupled logic, LVP ECL, low voltage differential signals, LVDS, high speed transceiver logic, HSTL, and common logic CML in physical layers files used in the serial link industry have quite different output level and input levels. Therefore, that will be difficult to interface different types of I/O file due to the different input and output level. Even with the same CML I/O buffer, if the TX chooses the supply reference CML with the NMOS differential pair, and the RX needs a ground reference CML with a PMOS differential pair, both common mode DC level still doesn't match, and the RX may degrade its input sensitivity quite a lot. So, how can we accommodate the different DC level between the TX and RX? Think about DC blocking images for 5 seconds. Correct. Just add a simple DC block capacitor to remove DC components of the signal. Output common mode voltage of TX VT, while the AC component TX output voltage swing is still passed to the RX. To generate the common mode voltage VCM at the other side R, we could add a resistor to the voltage source VCM underscore in, which would set the common mode voltage on the RX side of the AC coupled capacitor. So, the AC coupling can easily change the common mode voltage level even interconnecting different I/O files. Does that mean the AC coupling is the simpler approach than the DC coupling? Think about the bandwidth images for 5 seconds. Right, we must add the big capacitors of chip in the link, and that causes the system size quite bulky. In addition, more passive components either on the PCB or connected to cable will add more cost. Therefore, from a size and cost perspective, the AC coupling is not simple and as good as the DC coupling. How is the performance perspective? Is that simple? Right, be careful. We are not only adding the DC block capacitors to only remove the DC content. We were also adding the resistor for the DC biasing. Therefore, the C-R high-pass filter would set cut-off frequency at low frequency, which means if the signal has a low frequency content below the cut-off frequency, then low signal content would be removed. What does that mean? Think about the impedance versus signal frequency over pattern images for 5 seconds. Excellent. Intuitively, if you send a 1010 pattern, which is the highest frequency or next rate of a signal content, the capacitive impedance should be near zero with the proper size. Then the signal should pass well to the RX side without any swing attenuation. On the other hand, if you send a long pattern with a consecutive 1 or zeros, which is the low frequencies of a signal content, then the capacitive impedance should be big enough such that the signal would not pass to the RX side with proper and cause and big swing attenuation. Let's dynamically think about the consecutive ones or zeros one more time. While you send 10 consecutive ones, the capacitive impedance is ballpark Z1. And while you're sending 20 consecutive ones, the capacitive impedance is ballpark 2 times Z1. Therefore, the swing level at the 20th bits would drop ballpark twice of the 10th bits. The longer bits were sent, the longer swing attenuation would occur. So, we may call this swing attenuation phenomena a DC or baseline wandering. For example, if a DC block capacitor was not big enough to make the cutoff frequency too high, you will see the DC wandering with just a few consecutive ones or zeros. Of course, the DC swing will drop and the BL rate will increase. In addition to the long size of the AC coupled capacitor, what else will cause the baseline wandering? Think about the random data images for 5 seconds. Bingo! If the truly random data was sent during the data transmission, a very long consecutive ones or zero may occur in the link, even though the probability is low. Then, there's no practical AC coupled capacitor size to avoid the baseline wandering. What can we do to mitigate this possibility? Right, we just need to avoid the truly random data by data encoding trick to limit the maximum consecutive ones or zeros, such that the lowest frequency of the encoded data is well defined and was specified in most protocol standards. For example, the PCIe Express interface would even define the coding, and the AC coupled capacitor value must be between 75 nanofarad and 200 nanofarad. But there's a subtlety in the encoding tricks. Even though we could limit the maximum number of consecutive ones or zeros, some coding still has the DC wandering issue. Can you think about the DC drift image for 5 seconds? Correct. The encoded data must be DC balanced, which means the number of zeros transmitted must be the same as the number of ones transmitted through the AC coupled capacitor. Otherwise, the DC wandering could drift the logic 1 or 0 to a different swing level as shown here. Again, many data encoding tricks such as matrix coding to provide DC balanced data stream. For a clock signal with a 50% duty cycle, it should be intrinsically DC balanced. Since the AC coupling C-link will provide the most flexibility to make any TX and RX to be compatible with different file or system arrangement. The encoded data is also preferable to achieve a reasonable maximum long-run AC capacitor value and DC balance data in most protocols. Therefore, the AC coupling C-link is the most popular interface. Do you see any other benefits? Think about the reliability image of the disconnected interface for 5 seconds. Good. The cable or a median in the link could be pulled out or disconnected if the link was connected in a DC couple, there is a reliability risk that the TX driver could be shorted to ground accidentally and cause damage. Therefore, the DC isolation may prevent any reliability risk inherently. Another example is the RX reliability can be mitigated from a big TX output swing of DC current to the AC couple capacitor. Here is a summarized image of why we may need DC coupling or AC coupling between the TX and RX in any serial interface. The simplest serial link interface is DC coupling. Just simply connect the TX and RX through a PCB or cable. However, the DC coupling should have the DC constraint between the TX and RX. So, first, the common mode level should match to make sure both TX and RX would have the optimal operating point and the best performance. Second, the RX large output swing or current should not cause the RX reliability issue through the DC coupling. Last, pulling out the cable or media must make sure the TX output path runs short to ground or other risky DC path to damage the output device. If all the above conditions can be met, the DC coupling link should be the simplest without adding the DC block capacitor, RX input common mode generation, and encoded DC balance data constraint. Therefore, the design overhead and cost would be minimized in the DC coupling link. Unfortunately, in reality, there are too many different types of I/O buffers used in the serial link industry, and that would be difficult to interface different types of I/O files with different input and output level to accommodate the different DC level between the TX and RX from different vendors. The AC coupling link is a must. Unfortunately, not only a bulky capacitor, but also the baseline or DC wonder would be the showstopper issue. Hopefully, in most protocol, the data encoding may not only limit maximum long run, but also achieve a DC balance, such that the DC wandering is removed with a reasonable capacitor size. Other benefits of the AC coupling is the DC isolation, which would avoid the TX to get shorted to ground accidentally and cause damage. Furthermore, the RX don't have too much reliability issue from the TX large output swing or current. Lastly, the AC coupling link seems to be the most popular approach. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.